Hi, my name is Joe Barnard, and this is the engineering cut for Scout F. Scout F is a model rocket that I've been working on in one way or another for the last 7 years, and I finally was able to land it propulsively like SpaceX or Blue Origin this summer, and I'm really proud of it. The good news about that is that I got to put together a really fancy, well-shot, well-cut video that, appeals to a lot of people. The bad news is that avoids a lot of the really cool nuance of an engineering project like this. I want to be able to talk about all of the design decisions that I made and all of the nuances that led to those decisions. And that's the point of this video. This engineering cut is a chance for me to pull back the curtain as much as I can and just talk about how this rocket got built, how the design happened, and then all of the lessons that I learned along the way that wouldn't otherwise fit in a super flashy video. So that's what we're here to do today, and let's jump into it. Actually, 2 more things before we get started. If you're interested in a specific system on Scout, maybe it's avionics, maybe it's landing legs, maybe it's thrust vector control mounts, who knows what, if you scroll your mouse or your cursor through this video, you'll see that it's split up into different chapters, and you can just watch one of those without the context of the others, and it will probably be the info that you're looking for. And the second thing is that if you want to build one of these things yourself, I have put all of the CAD, like the step files, so that you could print or manufacture the parts for this yourself. I've put those up on Patreon, and the link to that is in the description down below. Okay, with all of those things covered, let's actually get started now. The first thing we're going to take a look at here is the CAD for the vehicle. So I've got the design up here. It's a pretty rough sketch. Not everything is 100% accurate, but I figured we'd go through. We can go through top down too. Starting with the nose cone up here, I came up with a roughly ogive shape. Ogive, I'm not sure how you pronounce it, but just a shape that looked nice to me. We're not going fast enough here that aerodynamics are really a concern. There's definitely drag on the vehicle, but we don't need to optimize nose cone shapes. It just slides in. It's a friction fit here into this 3-inch or 74 millimeter tube. And for the first flight, I 3D printed it with, I think, a little bit of infill. And for the second and on flights from there, I printed it with just one shell layer or one thin layer, spray painted it white. And so it is incredibly delicate. Okay, so this is the actual nose cone here. There's actually an internal layer and an external layer in how this is modeled. You could print this in vase mode. I think that's a thing you could do. You could print it in vase mode. But basically, this is now something like 10, maybe 15 grams with just PLA plastic. And it's good enough. Moving down the vehicle, the next thing you'll see here is the reaction wheel setup. So I'm going to turn off the airframe. There we go. So now we have no airframe. This is the reaction wheel setup. So this is going to control, or this does control, the roll axis of Scout F. This is a little 12-volt DC motor. This is something you'd find in a regular Arduino kit or an electronics kit, some type of maker kit. I picked it because it's cheap and I knew it worked. Between Sprint and Scout and the little micro 3-stage TVC rocket that I did, these 12-volt DC motors have been just fine. As I've said about 1 billion times now, we're not interested in controlling the roll attitude so much as the roll rate. We just don't want to spin up a whole lot, so we need something to resist that. This mount and wheel and all of the parts here was originally manufactured out of aluminum. All of this stuff is just 6061, and I was looking to get more experience with the mill that I'm starting to work on. So the wheel was aluminum and the housing was aluminum. The housing didn't need to be aluminum though, and so after Flight 1, I realized I needed to really dial in my mass budget, so I reprinted the housing for this out of PLA, polylactic acid, and that reduced the weight quite a bit. Continuing to move down here, we have the Avionics mount inside of the airframe, and it's really close to the bottom. You'll notice that the vehicle is sort of distributed in a little bit of an odd way. We've got the nose cone up top, which is extremely light. We've got the reaction wheel here, and then all of the big party is really happening down here. 90% of what needs to happen on the rocket is happening in this bottom section. That's because we want to keep our center of mass or our center of gravity really low on the vehicle. So it's a conscious choice, and it has some drawbacks that we can talk about in a little while. But basically, the avionics mount goes here, and it's not modeled in this CAD right here, but we actually take one of these carbon fiber spars, and we stick it out of the top of the avionics mount, and that's where we house the telemetry antenna and the GPS antenna. Longtime viewers of the channel will know that I sometimes have trouble getting telemetry and GPS to play nice together. Even though they're on vastly different frequencies, they can fight a little bit. So we put these things on a pole that extends from the avionics mount, and that actually has helped a whole lot in improving signal for both of those devices. The landing legs here are modeled in their up position. I actually have them modeled in the up and down position. Here we go. So this is legs up and then legs down. You could put these on like proper hinges and actually model the assembly correctly. But the legs are not modeled too much. The biggest detail part is really this leg base here. We're going to talk about this more in the landing leg section of the video, but this leg base it's a lot. We'll talk about it more. Just stay tuned. Okay, so we've got the legs here. We've got the leg strut, and then inside here, you'll start to notice that the strut and the TVC mount are actually attached with the same screw. I'm going to go ahead and turn off this airframe piece so you can sort of see through the vehicle. So if you see what I mean, there's this ring. This is all aluminum, 6061. There's this ring that takes the brunt of the force of the struts. This is when we touch down, there's a lot of sort of compression load on these struts, and it goes right into this aluminum ring. The TVC mount is designed to be attached at this same point. This is true for Flight 1 and Flight 2. We did use this TVC mount, and it was attached here. But for Flights 3 and onward, we actually moved the TVC mount, and we'll talk about that in a little bit too. In terms of the mount itself, I've got it isolated here. So there's a bunch of stuff going on. We have 4 servos involved in this, and that's because there are 2 systems. One of them is actually gimbaling the motor, so that's pointing it in different directions, and so that's this servo right here, and the one that's in the back right here. We have it set up in what I like to call an onion gimbal, which means there are 3 parts. There's a sleeve and an inner gimbal part that actuate on one axis. I think I actually have the joint set up for this. Do I? No, I don't think I do. Either way, we can rotate the inner gimbal and sleeve on one axis, and then we can rotate the inner gimbal and outer gimbal on the orthogonal axis, or 90 degrees to the other one. So you get the full range of motion, you don't stress any servos, and although it costs a little bit more space than doing them in the same sort of gimbal setup, it's an approach that I like. This mount got used for Flights 1 and 2, as I mentioned, and then we redesigned a different mount for Flight 3. I promise we'll talk about that in a little bit, but before we get to that, when we go down here, you'll see there's the attachment for the other motor. So this is the ascent motor on the bottom, and the landing motor is attached into the mount here. We just use like a friction fit for that. But the ascent motor gets this weird sleeve-looking thing that attaches to the throttling mechanism on the landing motor. So this is a section view of what the TVC mount looks like, which means we sort of just like intersect the CAD and look inside of it. So we have the 2 servos here that are actually controlling the throttle arms. I'm not sure why they're not showing up here, but you'll see them in a little bit. We have 2 throttle arms that move in and out. You've probably seen this by now. And these are the servos that control it. They're just attached directly to the motor with a little bit of a sleeve assembly. And part of this sleeve assembly provides a decent interface point for this ascent motor attachment thing. It's a very passive attachment, but what we want is that when the ascent motor is pushing up against that throttle section, we want really good contact. That ascent motor can't be like wiggling around. It doesn't look that smooth in this model, and I think it's not. I think it's because this model isn't fully up to date. We have a second model of all of the throttle mechanism stuff, but these seat really well together. Once you factor in all of the print tolerances, these things seat really well together, and it allows the motor to also slide right off. So on ascent, you could whip the motor around a bunch, and as long as it's burning, it will stay seated against the landing motor. But that's sort of the reasoning behind that. You can turn analysis off. And that's pretty much the thrust vectoring mount. Of course, that is not the full story, though, because we made a second TVC mount after Flight 2. The idea was that there's a lot of wiggle in this design right now because it's printed out of plastic. And so what I wanted to do is make an entirely aluminum TVC mount. I'll just say here, this approach, the decision I made to do this was a little bit misguided. I partially wanted to just get a lot of machining experience, and I thought it would be fun and interesting to try and challenge myself to make an aluminum TVC mount. Ultimately, I don't think it was worth doing. You could totally get almost exactly the same results with plastic. The real problem showed up with the servo horns here, which are modeled in gold. These were really, really bendy on the BMS A10H servos that I really like. These are the fancy Bluebird servos. And upgrading to a metal horn servo would have fixed probably 90% of the problems that I had with the sloppiness of the mount. That said, let's look at the metal TVC mount. I've got it modeled here, and you'll notice it's a little bit different, and there are some parts that aren't showing up exactly as I want them to. This is a little bit more accurate. I moved over to these HV93i servos. I believe that's what they're called. But these are MKS servos. They are just gorgeous, and they're like $80 a piece. They're incredibly expensive, but their response time is very, very good. All of the internal gearing is metal, and they provide these really high tolerance arms with their servos, or you can buy them separately, that are also metal. Also, MKS produces a bunch of actuators that I want to use in the future, and so it was kind of like well, I know I'm going to be using this down the road, so it makes sense to get some experience with it. Either way, let's walk through this mount here. It's the same type of design fundamentally as the other TVC mount, but we've changed a few things. So it is an onion gimbal, but we've changed most of the screw hardware to M2 instead of M3.5 because aluminum is a lot stronger than plastic, and so we can afford to really cut down on the amount of material. The mount still is a little bit heavier than the plastic version, but it ends up being just as strong because all of the parts are metal. Another thing you'll notice is that the push rods here are just big pieces of aluminum. We're not using that steel wire anymore. That was another source of the springiness for the past mount, is when you use these little steel wires with Z-bends in them, the Z-bends end up acting, I mean, they are springs. It's pretty much you're just adding a spring to your system. So the solution was kind of brute force it, design in a piece of aluminum that sort of press fits or screw fits or friction fits into these like actuation points on the mount. So we've got an attachment point here, and these right here, although my model is kind of freaking out, but these are very rigid. They're not going to provide any springiness to the mount. There we go. Can reset the model. In terms of interesting things, there's not a whole lot else going on with the mount. I did opt to move the servos up to the top. So another difference between these two designs is that the servos are no longer on the bottom of the mount. And this is important because it really improves the rotation point. Right now, with this setup, you're using this tiny little servo to whip around this big set of motors, comparatively speaking. So when we move the setup up, I don't think I have the ascent motor set up in this model, but right here, we're sort of actuating in the middle, or at least a little bit lower than the middle of the motor. So this is a pretty even distribution because the servos have moved up top, and we can move the throttling mechanism much closer to the TVC mount. So it improves the dynamics generally just because of how it's designed. But then also the metal helps quite a bit. Same throttling mechanism. You can see the throttling arms here. Man, my model is not happy. Okay, and the only other thing that I did here is add this little piece. So this is an interesting idea that I had when I was trying to figure out how we could secure this mount into a cardboard airframe and have it take a little bit of shock vibration without ruining the holes in the airframe. So let's go back to this design here. What happens when you land the rocket and the legs put a ton of force into this section right here? If it's a cardboard airframe, every time that happens, you're going to crunch the cardboard just a little bit. And the holes that are designed to hold the landing legs and take all of that force in the cardboard airframe, they're going to rip just a little bit every time. That ended up happening a decent amount on Scout. And I thought about the same thing in regards to the TVC mount. If you want a mount that is predictable and isn't going to slide around within your airframe, especially if the mount is mounted at the same point as these landing legs, that's going to happen. You're going to end up with misalignments that you don't want. So what I did here is I modeled these little pieces that basically go on the outside of the airframe. They've got these little points on them, these little grippy guys. And then when you screw in the TVC mount, so these holes right here, these are threaded. So the screw can grab these holes and it pulls it pulls this piece into the airframe to grip the airframe really hard, and it almost like digs into the cardboard. And once you get those joints really tight, you're not just putting any force from the mount into the hole where the screw goes. You're distributing it across all of these little grippy guys. This ended up working very well, but the important thing is to remember that you need to screw those in very tightly. It's really hard to align them all at once. It's a lot harder to see the hole and like get the screw in the right place. And that did bite me. It bit me in the butt one time. I can't remember which flight it is, but we had one flight where the mount was misaligned because I aligned the TVC mount at my house. So I calibrated the mount, made sure it was centered, and then I tightened these little grippy guys in. I tightened them down after aligning the mount, and that changed the alignment. So when we lifted off, the rocket like veered to the aft a little bit. Okay, a couple more things to talk about with CAD here. So we've talked about the rocket. The aluminum TVC mount ended up getting mounted lower than this plastic one. So we mounted it a little bit closer to like here where my mouse is. But that pretty much covers it for the rocket. The landing legs are made of carbon fiber. I ended up including some dampers at the end. We'll talk about this when we talk about the landing legs specifically. But now we can move down to the launch pad. So I have the launch clamps modeled here. I would have loved to use launch clamps on this rocket, but it was not really possible in the current configuration without a decent redesign. And I didn't want to spend time doing that. So I figured, you know what we'll do is we'll just prioritize flying with no wind, and we'll be really careful with the rocket beforehand. So there are no launch clamps holding the rocket to the pad for Scout F. That's why in some of the setup footage, you'll see that there are these like trigger clamps all around the top of the rocket, which is to prevent a gust of wind from possibly tipping the rocket over before it's ready to go. Either way, the other important thing to do with these types of rockets, especially if you are doing dead reckoning like Scout, is getting a really good initial attitude estimate. And so you can do this in two ways. You can either measure really precisely what your angle is and put that into the rocket and tell the rocket you're at exactly 1.875 degrees pitched in this direction, or you can say, assume you're at 0, always start at zeros across the board, and then I'll just make sure that the pad is really level. And that's the approach that I ended up taking here. So this big piece of metal right here ended up getting milled out just for this. I've got the axes labeled here too, and these holes right here, these are threaded. So what you do is you take these M3.5 screws, you screw them down in there, and then as you tighten or loosen the screws, when they connect with these this big yellow plastic piece here, you actually tilt the table one way or another. This would be better with 3 holes because with this you can potentially get one of these holes misaligned, if that makes sense. But it would be better with 3 holes. I modeled it with 4. It works with 4. I'm not a perfect engineer. That's kind of the situation there. And that pretty much brings it to the end of the CAD section, I think. We've got the launch clamps, we've got this little launch table base thing, we've got the table itself, and then we've got the rocket. So let's move on now. The next thing that we're going to talk about is simulation. Okay, besties, it's time to talk simulation. So generally speaking, there are 2 types of simulation that I did for Scout F. One type is about the stability of the vehicle, so we're talking about attitude rates. We're also going to talk a little bit about horizontal position and velocity. That's one type of simulation. The other type of simulation is all about throttle control and altitude. I split these up for reasons that you'll see in a little bit. And before we get into it, I have to impress upon you how deeply ashamed I am of how poorly this Simulink model is set up and organized. With that said, this is the simulation for not altitude, but just position, velocity horizontally, and then vehicle attitude and vehicle body rates. So let's talk about what's going on here. I did all of this in Simulink, by the way, and that's one way you could do it. You can write a simulation like this in Python. You could write it in C. You could write it, I don't know, you could maybe do it in like HTML. You can do all sorts of stuff with how you want to simulate. Honestly, I know a lot of people who use Microsoft Excel or Google Sheets. You can do it with that as well. Either way, the point here is that while I'm using Simulink, you can accomplish these things using a lot of different tools. In the top left, we have our tuning parameters. There's going to be some stuff here that I explain and some I don't, but the tuning parameters makes a lot of sense. Here's where we import our different gains for the control system. So we have our K matrices, K1, K2, and K3. These go into these blocks that allow us to push these matrices all over our Simulink setup here. We also have cross range, which is the amount that we're going to divert. Basically, this is the number of meters that the landing pad is to the side. Ultimately, for Scout F, I ended up ditching the landing pad, but initially when we designed it, I designed it to be able to target a point on the ground. We have the moment arm of the vehicle right here, which is represented as a fixed value. Even though it's not fixed in real life, it does move around a little bit. It's not a thing that I felt was worth like spending a lot of time on. Misalign 1, or just any misalignment here, this is really important. The TVC mount is never going to be exactly centered, right? You can look at it, you could use a laser level, you could do all of the stuff that you want to try and center the mount, but you're still going to be off by a little bit. In order to fix that in flight, we have an integrator term. So if you think of like a PID, this is just the I part of the PID. We have an integrator term that looks at our attitude or our attitude rates, and then it calculates the misalignment that we have in the mount. I'll show you how that works in a little bit. But basically, this is we're telling the simulation that our mount is misaligned by negative 0.2 degrees, and we can change this. Mass, this is mass in kilograms, it's just 1. That ends up getting changed in the simulation anyway. And then we have our two F-15 thrust curves here. I have them labeled as F-15 real TC, but it doesn't matter what they are. The way that we're triggering the second motor is a simple delay, and then we modify it with this throttle value. You can actually see, though, the PID for the throttle control is not connected up to the simulation. That's because while I initially attempted to run all of the throttle control stuff through Simulink, I found it a lot easier to run the throttle control simulations directly on AVA using the software in the loop functionality that I built for Scout E. And that's been so helpful, honestly. So the throttle control stuff is mostly depreciated and is not affecting much here. Either way, we've got two motors that burn, and if I bring up a plot here, this sort of shows you the motor burn times. There's a couple other things going on in this plot. This is basically the attitude of the vehicle, and then the thrust, which is a little bit modified. Don't worry too much about it. This is the heart of our simulation here, which is a block that Simulink makes called the 3DOF, 3DOF, 3 degrees of freedom. What we're looking at here is basically altitude and then movement to the side, but it also represents body rates, attitude, horizontal rates and velocity, horizontal position, and it generates all of those. It's just a bunch of physics stuff in here. It generates those with the upward force, the side force, and then moments on the vehicle, moments in the body axis. Okay, so why don't we zoom out just a little bit? Essentially, the way this works is we run it in a big loop here. So why don't we start off with this block and then move to the side? This block gives us our theta in radians. It gives us our radians per second. It gives us our x and z position in meters, and then our x and this is our x and z velocity, and then our accelerations. We take these values and we create a state vector. So I use a vector concatenate block here, and this is our state vector. So when we talk about state space control, or full state feedback control, that's what we're doing here. We create our state vector, and then we sum a few things in here. This is a whole mess. Again, I want to apologize for the lack of cleanliness in my simulation here, but this is the sim. So we've got what we've got here is a set point generator. So we're generating like the target commands for what the set points are. I'm not sure exactly what's happening here, but we've got a set point that goes up to 2 and then back down to 0. Hard to tell what's going on, but basically this is where our set points come in, and then we also add in some sensor noise. So we inject a little bit of noise into, I believe this is the attitude or the body rates, depending on where in the vector you're adding it, but we're just adding in a little bit of sensor noise here. Here's a really zoomed in view of that sensor noise, but we're trying to trick the control system into thinking that it's flying, and we want to see what a little bit of noise will look like in the control system as well. So adding a little noise is helpful. Our signal then comes in here, so this is still our state vector, and we matrix multiply it with our K matrix. So this is our gain matrix, right? These K matrices are scheduled down here, so we have our first K matrix at liftoff, and then we just use a series of delays and ones and switch blocks to switch these different K matrices. So we go Kmat to Kmat 2, and then Kmat 3. We actually put Kmat 3 in there on ascent for a second. Kmat 3 is all about stabilizing the attitude rates of the vehicle. So at the very end of the burn, on ascent, we are trying to stop the vehicle from tilting. I think a lot of launch vehicles do this right before their staging function activates. So before you basically give up your control of the vehicle, you want to focus exclusively on making sure that the vehicle isn't rotating. We're doing that here with these gain matrices. Okay, so now we matrix multiply with this, and you'll see there's also something that comes out of the bottom here that I labeled integrator. What is the integrator? Great question. So the integrator is what deals with that misalignment that we talked about earlier. What we do is we take this down here in a really sketchy way. We pull it into this like demux block, and then we just have a discrete time integrator here with a huge gain. I think it's like 160 or something. Oh, just 60. This is sort of a hacky way of like finding out what our misalignment is by knowing the mass of the vehicle, knowing the general acceleration, knowing what the flight dynamics look like for the first about half second of flight, or 100 milliseconds of flight. And so this scope here shows us what the rocket is thinking. And if you watch really closely after liftoff, as the vehicle lifts off the pad, it's going to start tilting in a certain direction, even if the mount is centered, because there's some misalignment. So if we look at that tilt really close, we can correlate that tilt by just multiplying it. We just have some gain in this integrator. We can look at that tilt and integrate it up until a certain point, and it will arrive at our misalignment so that we can add that back into the mount and basically cancel out any misalignment. So we center our mount in the first half second of flight or so by looking at that tilt. That's what's happening here. So you see this line move up to negative 0.2, and if you remember, negative 0.2 is what we set our misalignment at. So if I were to change that negative 0.2 to, let's say, positive 0.5, I'm going to do that now, get rid of the negative. I'm going to run our simulation again. It's going to take a hot minute. Give it a second. And the simulation's running, and it's done. I'm going to look at the scope again. When it comes up, look at that. Almost 0.5 degrees. The integrator has figured out, using that tuned gain, what our misalignment is. So that is what this little section represents here. Coming over to the left is where we deal with the thrust vector control subsystem. There's a lot going on here. Fundamentally, it's pretty simple, and I model a little bit more than we need to here, but let's talk about it. All of this stuff here is dealing with the torque commands that come out of the matrix multiply block. So when we do our matrix multiply, when we basically multiply our state vector by our K matrix, the output that we get is just two elements. It is the X and Y, or it's the Y and Z, technically TVC servos, but it's not the servo command that comes out. It's a torque. The control system demands a torque on the vehicle, and we can work backwards, knowing our current acceleration, to generate a TVC angle from that torque. So that's why we have these A sine functions. We're multiplying by the mass. We're looking at our acceleration. I'm not going to go too in depth on this, but there is a way to work out that torque, or work out that TVC angle to get the torque that you want. Okay, so that's what this is dealing with here. We also have a zero order hold. We have a few of these. I think these may be a little bit redundant, but we have a few zero order holds. And what a zero order hold is, a very hard term to say, is it basically creates it takes a continuous signal and it turns it into a discrete signal with a sample time. So our TVC mount doesn't update at 3,000 hertz. There's a certain speed that you can drive this TVC mount, and especially given the wiggle that we were seeing, I had to play around a whole lot with the TVC update rate. So you have to pick an update rate for your TVC mount that your servos can handle so that you can accurately control your vehicle. Anyway, so that's what the zero order hold does. If you look at the input and output, I can actually just show you here. Here's an input. There's another input. And when I open this up and we run the simulation, it might take a minute because my computer's feeling very slow today. Running the sim. Okay, now let's do this. Why don't we zoom in on, let's say, this section. And if we get really close, you can see what that zero order hold is doing. So we have a continuous signal. That's our blue signal. That's the demand from the control system of that much torque. And then we have a discrete signal, which is the output from the zero order hold. So we go bop, 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 bop. It's like a staircase. And that's what actually gets sent. That's representing the discrete function that we call in our code that says update the TVC mount. Okay, moving on. So we've got our zero order hold. We sum in the integrator here as well. So the integrator ending up being like 0.5 or whatever it figures out the misalignment is, that gets summed into the output for the TVC mount. And then there's some really sketchy, hacky stuff that I hate that goes on down here. I'm not going to get too into it. I'll just tell you that it turned out one of the ways that we were able to fix it in software in terms of solving the wiggle problem from Flight 1 is we put a moving average on the TVC output. Do I think this is a good idea? Not really, but it does work. It works well enough, and we just needed to get this thing to work. I built the whole vehicle and then found a problem with it. I would rather be able to fly that vehicle with a hacky solution than redesign it. So that's what this is doing. We're adding a small moving average to our TVC command, and I believe you can see it in here too. Only on ascent too, because the dynamics problem is only on ascent. So what's happening here is the blue signal is our discretized command in terms of degrees for the TVC mount. So this is what we're commanding of the mount. And the moving average is what gets sent to the mount. There's a command that would get sent to the mount, which is in blue. And then we actually end up sending the averaged command to the mount, which makes the mount move a lot smoother. It's a lot less jerky. We're not getting these discrete spikes so much, but it does slow down your control system too. Okay, up here we have Z direction servo, ALMNTTF. This stands for the aluminum mount transfer function. So this is a transfer function that we're pulling from our MATLAB workspace that I generated using the system identification toolbox. I stuck an IMU on the TVC mount, and this transfer function represents the dynamics of what command you would send to the mount, and then what command the mount would actually move to, or what angle the mount would actually move to. So if I put a scope here and we compare the input to the output, once again, my computer will take 6 million years to actually run this simulation, but it'll show you what the transfer function is doing here. So let's say this is actually this is a great example here. There's a big discrete spike that we send to the mount. That's this yellow line, right? So we say, I want the TVC mount to go slamming to 5 degrees, but the mount's not actually going to do this. So the blue line represents the signal delay. It represents whatever internal electronics in the servo are going to slow that actuation down. It represents the sloppiness of any type of sloppiness in the mount. It represents any resonant frequencies. That's what's happening here. So we're trying to model the actuator dynamics. Okay, moving on. We have some saturation stuff in here too. The saturation is basically just representing the limits that we have in our system. We can't gimbal to 30 degrees. We can gimbal plus or minus 5 in some cases. In some cases, you can go to 6. So that's the saturation block here. We convert our radians, our degrees to radians, because that's how this block likes to work. And then we convert this TVC angle back into a torque before we put it back into the 3DOF block. So we've been working in degrees all down here. We converted from torque to degrees, and then from degrees back to torque. Okay, and then this is just converting our sideways forces to velocities so that they can convert to position too. We have this fun, cute little section here called bump. So what bump does is it just has a tiny little blip in it. Why don't we do another scope here, and I'll show you what I mean. So bump, before we put it through this gain block, run it through, and you'll be able to see what this is. Ba-ba-da-ba, please run the simulation. Oh my goodness. Oh, that's weird. Okay, well, it doesn't matter. Anyway, we only do bump once in here, and I'm realizing this may have been affecting our simulation more than I thought. That's probably something I should be looking into. Either way, bump is trying to represent how we don't have fins on the top of the vehicle. So when I showed you that plot earlier, it's a plot of attitude and then just a rough representation of the thrust. See how there's like some turning motion here. This orange line is the vehicle attitude in degrees. So we go almost up to 5 degrees in our coast phase, and then we start going back down. You can change this bump value, and it will change how the vehicle, like, in theory, rotates. So I'm gonna make this value negative now, and you'll see it rotate in the other direction during that coast phase. That's sort of the point of bump, is so that we can simulate, like, can the vehicle, look, the vehicle can't recover from this. We rotate all the way to 40 degrees, and it's just like freaking out trying to get back to upright, and it doesn't work out that well. So that's what bump represents, is just knocking the rocket around a little bit, so that on the motor startup, if we start up at 30 degrees, can we recover from that? If we start up at 40 degrees, we obviously can't. And that's pretty much the simulation here. I tuned these gains all by hand in terms of the different K matrices. They're all tuned by hand. You could use LQR for this stuff, but there's so much nuance in the actuator dynamics and like this moving average nonsense that I found it easier to just tune things by hand. This simulation, though, this needs to die. This is insane. This is like the work of a crazy person. It's such a mess here, and really we should be working with much more cleaner subsystems and things like that. But anyway, that's the attitude simulation. Why don't we look at a much prettier thing, and that's the throttle simulation. Okay, now it's time to talk about throttle control. To begin, we need some type of jumping off point. A common theme that you will see on this channel again and again is that I don't always go for the solution that is elegant and beautiful and perfect and should work every single time. There are so many problems to solve with these rockets that I'm often picking solutions that I know, you know what, it's gonna work well enough, send it. In the spirit of that, I'd like to show you how I came up with this weird throttling approach that has seemed to work well enough. It clearly doesn't work great, but it has worked well enough. Okay, check this out. So, in May of 2019, I did this landing test of the Echo landing vehicle. So I'll just play the clip for you now. But basically, the rocket falls from a drone for about 30 meters, turns on the motor, and it just happens to be almost perfect. It burns out like a half meter above the ground, maybe a quarter meter above the ground. You can see some other clips here. It comes down, it lands, and really what I'm most concerned about, I mean, honestly, with like good legs, it should have just landed, but what I'm most concerned about here is the altitude plot. So with every test, I record data, right? I'm always trying to record as much data as possible, and so I still have the data from this test. So in about February or March this year, I started gearing up for these scout flights, and in part of that, trying to make this throttle control stuff work, I took this data, I plotted it, and then I found a trend line of this like altitude situation. So let me show you how I have set this up. Make it a little bit bigger so it's easier to see. So right here, we're plotting our altitude, which is just a really rough barometric measurement. Gets even a little bit more rough when the motor turns on. You can also see the acceleration on the vehicle. You can see the drag creep up just a little bit here. Once we drop from the drone, start going a little faster. We have the peak of the thrust of the Estes F-15 motor, and then we also have a big shock when the landing legs come out. But you can kind of see what's going on, and you can see where we burn out here too, where we just like hover around the ground. Okay, so a few things that I've done here. The time is not the time on the vehicle. I have normalized the time right around the peak. I have normalized the time so that 0 happens at the peak thrust of the motor. And then I've also made a trend line here that follows the barometric altitude pretty well. So we've got this function up here, 13.5 plus negative 9.62 times x. X is the time in this case, so that's 0, 1, 2. That's seconds after the peak. 9.62, negative 9.62x plus 1.8x squared. And so it's a polynomial. It's a second order polynomial. I use polynomials all over the place. It's honestly, I think it's easier than a lookup table than having to like populate a whole table of data. Just find a line that fits pretty well, and you can use that line as a continuous way to pass data from like one thing to another. I don't know if that makes sense, but you get what I'm talking about. We make a trend line that shows where the vehicle should be at a given point in flight. Now, the important part here is that the trend line is relative to the time of the burn. So by this point in the burn, by like 2.6 seconds into the burn, you should be here. At 0 seconds, you should be at this altitude. The peak time is important because solid motors have a fixed burn time, right? You can't change how long that they burn. You can't change how long they burn, so you have to work within that constraint. And this is sort of the really hacky solution that I came up with. Also, ignore this trend line here, this red one. I think I was trying to like tune different stuff. You can see these rogue data points here, 9.5, 4.75. I think I was trying to like modify this trend line or something like that. Either way, here's our starting point. We have this trend line, and now it's time to take this trend line and use it as a set point for how high the vehicle should be based on the time in the burn that it is. I'll also mention that you don't have to fly a rocket like this. You don't have to do this test to get this type of data. Obviously, it's nice to have real-world data, but in the MATLAB simulation that we just looked at, you'll see these two blocks, out alt set point and out vel set point. These blocks basically record the simulation values, and then you could access them later. Really high fidelity stuff. So let's say we come up with a simulation that looks really good and the vehicle lands really smoothly through that simulation. It's very high fidelity. You could come up with a trend line like this from much smoother data, but it would be from a simulation. So you don't need to fly a rocket like this to get this data, but I just happened to pull it from this because, I don't know, it seemed cool that we could use some old data. As I mentioned before as well, we did try to do the throttle control stuff in Simulink. So I guess I'll just take a look at this and explain what's going on because it's a little bit more intuitive in here than it will be in the code. Basically, here's what happens. This right here is our altitude, and this right here is our altitude set point. So like any control system, we have our position, and then we have our desired position. We subtract the desired position from our position, and we get a difference or deviation. Shouts out, Missile knows where it is. We take that deviation and we put it into the PID controller, and this is the throttle PID. I think it's probably set up, it's set up at 100 hertz here. It's a discrete PID. And so we have our gains here, negative 0.1, negative 0.15, and these gains end up going into the throttle control system. One more thing that I do want to mention here, though, is that these gains are trying to output between 0 and 1, 1 being full throttle and 0 being nothing. They're actually capped at slightly different values. But the output that we want to give to the throttle control, it's a little complicated to describe this. Basically, our nominal throttle is 0.8 out of 1. So it's 80%. That's our nominal throttle. And then we add the PID command to 0.8. So actually the PID output, I think I have the limit set in here. Oh my goodness, please open. Here we go, output saturation. It can go up 0.2, so that's all the way up from 0.8 to 1, or it can go down negative 0.8, and that would take it to 0. That would close off all of the thrust. The reason we do this is that I'm a little bit more comfortable with the idea that we will have to cut more throttle than we will have to add. And we don't want to cut a whole lot because we do have to slow the vehicle down. So 0.8 seems to be a good normalization point where we wouldn't erode those paddles too much. And that's sort of how the PID situation is set up. Again, I don't think this is like the cream of the crop. I don't think this is a really good way to do throttle control. I will tell you, though, it produced results that weren't that bad. So why don't we take a look at a couple of those? Okay, so check out this clip. What you're seeing here, all of this data on the screen, it's all fake. It's not fake necessarily, but it's all generated by AVA. So what we're doing here is called software in the loop. It's a very weird blend of it right now because AVA is running its own software in the loop. But essentially, what you want to do with this is you want to test your flight software, right? And you don't want to test it in flight while you're burning motors and risking, whoever's nearby. So you take fake flight data or fake inertial cues and you inject it into the computer and say, do your thing, fly as if you were actually in the air. And that's what's happening here. During development of Scout E, the previous version of this rocket, I did a whole lot of work on creating this SITL functionality in AVA. So let me show you a little bit about how it works. Okay, so this is the code for AVA. This is the main loop. It's in C++. It's really in like Arduino, but you can call it whatever you want. In the main loop, we're calling a bunch of different things, and then we move through the different states of the vehicle. But the thing that I want to show you here is this function right here, or rather these two lines, 112 and 113. So on 112, we have a commented out function that is called SITL nav update, which is the fake navigation computer, and then we actually call nav update, which is the real navigation computer. The way that AVA is set up, we have three computers. There's an MPU, which stands for main processing unit. There's a nav, or navigation computer, and there's a telemetry computer. And so the MPU asks the nav for all of the navigation data. The nav is responsible for the IMU, the barometer, the GPS. It's responsible for the Kalman filter. And then when the MPU says, hey, I want to know where we are, it asks the navigation computer for those values. And that is what happens in the nav update function. But what we can do here is we can comment this out and comment this back in, and now we're running the SITL nav update function. And we're just ignoring whatever the navigation computer is doing. But from the perspective of AVA, from the MPU, it has no idea what the real data is and what the fake data is. So this is a pretty good way to do SITL for AVA. When we look at the SITL update function, we can see what's going on here. So if SITL is true, if we're actually running this, we run this at a simulation time step, which I think is like 200 hertz or 100 hertz or something like that. And we do a couple of the things here. If we haven't passed the launch time, don't launch. And then this is if we're launched, we can start running these functions here. So we've got F15TC, which is our F15 thrust curve, and it's represented as, you guessed it, polynomials, baby. It's just a bunch of discretized polynomials that I came up with trend lines that represent what the F15 thrust curve is like. I hate lookup tables, so I do it this way. Anyway, it's a pretty accurate representation of it. We got a bunch of ridiculous stuff here, but it works well enough. So anyway, we run this, and it allows us to test out our software. Okay, now, remember before when we looked at that spreadsheet, let me pull it up here, and we saw that I normalized the thrust curve around the peak, so 0 here, and then if we just call, what if x is 1, that's where the altitude should be in reference to the peak. So that's how we generate that altitude set point that tells us if we're high or low with the rocket. So what does that look like in real life? It looks like this. In our update state vector function, which is just updating where the rocket thinks it is in all of the states that we're trying to control, if system state is greater than 7, which is the landing burn start, we do xpos inertial MSP, which is x position in the inertial axis, or inertial frame rather, meters. I always put the unit of measurement in there, meters, and then SP is set point. So that's our desired altitude. And then there's this nasty polynomial in here, and we have a couple of different variables, but mostly it's just this, time since peak sec. So that is the time since the peak thrust of the motor in seconds. Now I hear you asking, Joe, how do you know the time since the peak of the burn? Great question. This is where we find the peak acceleration, and this is a function that was carried over from Scout E. A lot of this stuff is carried over from Scout E. A lot of the development for Scout F happened in 2020, basically. But this function, honestly, I don't know that I could explain it without looking at it for a little while. But we're looking at a couple of different gates here. We need to be accelerating harder than 6 meters per second squared. We need to have been 0.25 seconds away from the peak thrust. So basically, we're looking at our past data to see if the thrust is decreasing or increasing, generally speaking. If we pass all of these things, we hit this statement here, this series of statements, peak at this time, the command to peak time. That's the, if you look at this clip here, the command to peak time is listed as just peak time right there. This is important just for data on how long it takes between when you send the ignition command and when the motor begins its nominal burn profile. And then we have some variables in here that's going to allow us to set that time since peak sec, which is going to help us generate that set point. Okay. So we've got our set point, right? We have our set point, we have our time since peak set. Now we need to actually run the throttle command. That happens in this function right here called throttle update, which is a total mess. There are lots of different edge cases in which we want to open and close the throttle arms. It is not directly a PID approach. For instance, I'll give you an example. If you realize that you've touched the ground, you want to slam those throttle arms shut so that you don't hop the vehicle back up. So throttle update has a whole lot of stuff going on in it, and for simplicity's sake, we'll just skip it right now. But in SITL, what we're doing is we're running all of these functions with this fake navigation data, and we have the rocket command itself, we have the rocket try and land itself, and that's what this SITL stuff is all about. So I figured the easiest way to do it is just run the simulation. And if you want disturbances, if you want variances or things like that that you wouldn't get from just integrating a bunch of really smooth measurements, we have that too. In the SITL function here, or the SITL.h page, at startup, we set a couple of different variations using the random functions. We do random seed and read one of the analog pins, specifically the battery voltage pin. That reading is never going to be exactly the same, and it's going to give us a different start point in the random sequence of Arduino, so that in most startup cases, we are getting not true random, but like pseudo-random values. And then we add ignition variation times. So we have a variation of 180 milliseconds that we can go either up or down, not up or down 180, but it doesn't really matter. These are all details in the weeds here. We've also got ascent variation, so I couldn't tell you exactly what these things represent, but these are tuned to basically simulate a strong motor or a weak motor, things that would give you a slightly different flight profile so that you can, in real time, in real life, like Monte Carlo this situation. But yeah, no, I mean, I'm quite happy with the SITL stuff. It has proved incredibly helpful for things that are way beyond Scout too. For all of the HPR stuff I do, all of the high-powered stuff, I've got these weird polynomial curves that are now built up for, like Lumineer had an N motor, and I have an N motor thrust curve in here now. We used thrust curves like for Send It, right? For my level 3 launch, that gets an SITL run before too. Like any flight at this point, before I fly, I run a software in the loop test, and it's really easy because of Scout. So that is the throttle control section of simulation. We talked about the attitude control section of simulation. And now, since we just talked about throttle control, why don't we talk about some of the hardware, the characterization, the testing, and let's just jump into it. Before I arrived at this ceramic paddle solution that ended up working for Scout F, I tried 2 different solutions over the course of the months leading up to these first flights. The first solution, and I think the easiest one, if you can get it to work, is called Krushnik effect throttling. You can find some obscure papers on this and a little bit of test data online, but there's not a whole lot of really good literature about it. The idea is that as you extend a sleeve past the exit plane of the nozzle, if you extend it long enough, you start to get this weird interaction with the exhaust plume where you end up cutting off some of the thrust. Now, there's varied explanations as to how this works. I am not going to be the right person to explain that to you. And again, some of the literature on this is like really obscure and hard to find, but as far as I can tell, this happens because there's this turbulent interaction between the exhaust plume and this sleeve that you move in and out from the motor. I don't know that much more than that, but I do know that it has a throttling effect. So my goal was I have a bunch of these F-15 rocket motors in preparation for lots of flights. I can just sort of brute force record a ton of data with a ton of different designs and sleeve extensions and see if we can find some type of correlation. So that's what I did. In the fall of 2021, I set out to fire tons of F-15 rocket motors with these Krushnik sleeves. And as I fired these, I filmed them from lots of different angles, and I recorded the data on a load cell. A quick shout out here to the team at FreeFly, who make the wave camera. They also make a bunch of aerial imaging systems. They've been very generous in letting me loan out these cameras or letting me borrow them. So a lot of these really slow motion shots come from the FreeFly wave camera. So while firing these motors produced a lot of pretty footage, the data was less encouraging. Before we take a look at the data, I want to explain that we do need about 20% throttle range at a minimum in order to close the landing problem. This value was arrived at by running a bunch of simulations in MATLAB and Simulink, where I tried to simulate the expected ignition time deviation and ascent deviation. So basically, that's how high we go, including the variation of the different F-15 rocket motors, and how fast or how slow we can ignite that landing motor. And so that deviation is sort of what sets the limits on how much throttle control we need to make up for those deviations and get us back on a path that lands us just slightly above the ground. Okay, so that's all you need to know. You need 20% throttle range at a minimum for this very specific problem. The bummer here is that we definitely don't get that 20% throttle range. We can almost get to it with that green line. That's the 2 centimeter depth. You can draw some correlations between the depth of this Krushnik sleeve and the actual ultimate throttle percentage or the effective throttle, but these deviations are not that significant. I was really hoping for something more, and as soon as I started to put this data together and compare it with the different lengths of the sleeve, I kind of knew that this solution wasn't going to work. If you had a lot more control over the ignition timing of the motor and over how high you go, or maybe you're coming in from terminal velocity, so you're always coming in at the same velocity, something like this could work. But ultimately, I knew that the Krushnik sleeve is probably not going to cut it in terms of the amount of throttle percentage that you have versus the amount that you need. So we needed a new solution. The next idea I decided to try is essentially PWMing the rocket motor, or pulse width modulation. PWM is used to control servos, it's used to control lots of little electromechanical actuators, but the idea is that you have this fixed frequency pulse and you modulate the width of that pulse. So let's say that you turn the rocket motor on and off 4 times a second, but the length of that on period or the length of that off period gets modified. So you're still doing 4 hertz, but you're doing 4 hertz with like a... You know what? Why don't we just take a look at the footage and I'll tell you about it more. I figured the simplest approach here was just to shove a piece of metal in front of the exhaust plume. I gave it a little bit of an angle too, and this is where I started getting a little hacky about it, but you want to be really careful not to divert the thrust in any specific direction. You want it to go pretty evenly out. If you divert the thrust in a specific direction, you're creating a torque on the vehicle that the thrust vector control system is going to have to counter. So the less of that, the better. Also, really quick, I forgot to mention this, but the reason for that angle is that when the blocker is under load, the angle should basically become 0. This is why I was saying that I became hacky with it. That's just like, why don't you fix your design so that it doesn't deflect so much? But I was trying to design around that deflection. I'm not that proud of it. I arrived at this design in January, where the best mill I had access to was this little desktop CNC. So I could only make it out of aluminum, or specifically 6061 aluminum, which has a melting temperature that is far lower than that of black powder. I was kind of hoping that I could just beat physics on this one, and as it turns out, usually physics wins. When I tested this little blocker on the stand with a hot fire, it was pretty much no contest. The rocket motor chewed right through the aluminum. And worse than that, it not only chewed through the aluminum, but it started diverting the thrust very aggressively to the side because it chewed out a channel, not a clean cut through the aluminum. When you look at the test data from the load cell, it's clear that the aluminum blocker is working to some degree, especially during the first part of the burn. And you can actually kind of see it modulate the width of that pulse a little bit, but it clearly loses effectiveness pretty quickly. So if you had a much shorter burn, or you manufactured this aluminum blocker out of Inconel or some, super high temperature nickel alloy, this could work. That said, I'm not convinced this was ever a very good idea. It was just a solution that I tried. Okay, now it is time to move on to the solution that actually worked. This is the design that you're probably familiar with from Scout F. It's the two little ceramic paddles that clamp down on the thrust of the motor. So here's how this went down. After I did the aluminum blocker, I went on Reddit and just searched for, I actually went on Google and just searched for throttle control solid motors, and I came across this post from almost 2 years ago now, or I guess just 2 years ago. Solid rocket motor throttle opinions, and then this video that shows these little throttle arms that end up clamping down on the exhaust plume of the motor. And I was like, hey, that's a pretty nifty idea. I should scroll down and look what's going on in the comments. And it's me. I totally forgot about this. But yeah, I was a little confused by the thrust data, but overall the design looked really good. This person, Simple Robotics on Instagram, has actually been really nice. I talked to him over a couple of DMs a while back and asked if it was okay if I made a derivative of his design, and he said yes. So I came up with this. This is actually the second version of the design that I tried, but we basically have these two servos that control the throttle arms. I've got them linked in motion right here. This is the second version, I say, because the original version of this did not have this rounded edge here. It was just flat. The reason the edge is rounded is I felt like it would be better for erosion of the motor, and that turned out to be true. So let's take a look at some of the test footage. Actually, before we do that, let's talk about making these paddles too. So the servos are my favorite little Bluebird BMS A10H servos. You don't need servos that are this nice, but a really thin profile is great because this has to still fit inside the rocket tube, and thicker servos are going to impinge on your ability to have decent gimbal range. So I used those servos, and I used them in a 3D printed mount that's just plastic mount. The burn time on these motors is not that long, and so the heat isn't going to soak into that mount until well after the burn. So it actually works fine to just use plastic for that part. But the paddles can't be plastic because they see really high temperatures. So those are made out of high temperature ceramic that I found on McMaster. It's a pretty expensive little 1/2-inch block here, but it does work very well, and the paddles can be reused multiple times. We'll talk about that in a little bit. These paddles got milled on my little desktop CNC. Get ceramic everywhere, and you got to be really careful about not getting that dust in your lungs or breathing it, getting it in your eyes, any type of orifice, basically. You don't want that going anywhere. The paddles get some holes drilled in them. If you look at the video on this channel about solid rocket motor throttling, you'll see some of the struggles that I encountered in the process here, mostly just making sure to properly evacuate chips from when you're drilling. The paddles get mounted, and then I try to calibrate the servos so that they actuate pretty evenly. This is an important part with this design. You have to get that as close as you can, essentially matching the movement of the two servos. It's a little bit tricky to do, but if you don't match it properly, you'll see in some of the test footage here, you can actually end up deflecting the exhaust to one side, and you end up creating, as we've seen in some other approaches, you end up creating a moment on the vehicle. So you vector your thrust through this approach, but you don't really want to be doing that. What you just saw there is the first time that I fired those ceramic paddle throttle things, and as you can see, because this is the first, it still has that sharp edge on the inside before I rounded it off. But this is just a proof of concept, and let's look at how the proof of concept worked, which is it worked great. This is like amazing. Seeing this data gave me incredible hope that we could actually throttle these solid motors. So this is the first test from January 3rd of 2022. And you can see the servo command, which is just converted to like an arbitrary number. But the servo command in relation to the actual measured throttle, or the actual measured thrust, at least measured by the load cell, and then a nominal curve here in blue of just a regular F-15 rocket motor. And this totally works. Like, we can throttle almost down. This is like 1-2 newtons here, where it would normally be up to 15 or 16. So this was really encouraging seeing this. And now, of course, the question is, how repeatable is it? Unfortunately, because I wanted to change the design to the curved design, I did have to remake the throttle arms and then basically find a new baseline. But That's the next step in this process, is we have to find out how repeatable these things are. And that is exactly what I did. After a few weeks of working on a different project, in late February and early March, I set up a few more tests, specifically 3 more tests, to fire these throttle arms. These tests also proved valuable to determine if we could reuse these throttle arms. I had a sense that we probably would be able to, just judging off of these first few fires. The paddles don't really see a lot of erosion here. They definitely see a lot of heat, and most of the change in shape has to do with melting a little bit of that PLA plastic away from the servo mount. That gets on the throttle arms. It cakes the throttle arms. They get coated in, like, when the exhaust plume goes back onto the clay nozzle, some of that clay comes off and it goes onto the throttle arms too. But fundamentally, the ceramic doesn't erode away that much. So several of these tests, you'll see that the throttle arms don't start off as these clean white ceramic pieces. They start off really dirty because they've been fired before. The other thing that I did a lot of during these tests is measure the side force. You'll see a secondary load cell on some of these where I'm trying to measure how much off-axis thrust are we getting. In the test that I showed earlier, when we had that deflected thrust angle, I didn't have the side load cell there. But just in case that reappeared, I wanted to measure what the side forces were. So we're measuring on 2 load cells for every one of these tests. So the good news is that when we take a look at this data, we can see it's pretty repeatable. There's definitely some variation here. There's definitely some range. This actually includes the original data that I fired with the square-edged throttle paddles, because that ended up being close enough that it seemed like valid data that we could work with. The difference here is not that great. But over the course of 4 different throttle firings running about the same servo commands with slightly different alignments for each one, and of course slightly different rocket motors as well, it turns out that these throttle paddles are pretty repeatable. I didn't have good documentation on which paddles were brand new and which weren't. But this range, even with this range of a few newtons here, since we're actively controlling the descent, it's okay if we have a little bit of error in our throttle percentage. We can use an integrator term to pick that up, or just some higher proportional or derivative gains. This plot that you see here is showing the side forces that are generated during these throttled tests. This is measured in newtons. On average, the side forces are pretty low, not that bad. So 0.3 newtons seems to be about our peak here. We have a weird blip in, I think this is just a measurement error, sensor error with the load cell. But generally speaking, the side forces from this throttling approach were really low, and that was awesome. I was pretty worried about that. And it turned out not to be an issue. This also is true in terms of the flight testing. Those side forces turned out to be pretty insignificant, which is, it's very good. It's a really good thing. Okay, there is one last thing we need to talk about here in reference to throttle control, and that's how do you go from commanding a throttle percentage to writing that value to a servo? So one more time, just look me in the eyes, okay? We're not flying a crewed vehicle. We're not flying some super high-stakes scientific payload. This is a model rocket. I'm allowed to make hacky decisions, okay? So with that said, here's how we do it. There are 2 steps, okay? First, we have to take the throttle percentage and we have to turn it into a distance between the paddles in millimeters. That's at least a really intuitive way to make sure that you can set up these paddles in any scenario, regardless of like how your servos work or whatever, and you have to convert it to a distance. And then the other thing is you have to convert that distance to a command on the servo. Okay, so let's start with the command on the servo part. We'll work backwards. So this is a plot that I made, or a chart that I made, whatever you want to call it, called command cal versus distance in millimeters. Command cal is basically, we have some value that we write to the servo. This is not really in degrees necessarily. It sort of has a reference to, it's sort of in relation to, like, honestly, don't even worry about it. It just is like, it's an arbitrary number. Command cal can go up to like 600 or 800, and it's we add it to the closed point on the servo. So the closed point is like some value, and then we subtract 200 or 400 or 600. And then it translates into a distance in millimeters between the paddles. So when you write one of these commands to the servo, it translates to, let's say, 4 millimeters between the paddles, or 6 millimeters between the paddles, or 8. And so we take all of this data that I measured and we find a function that defines it, or that can really roughly approximate it. So right here we've got this nasty polynomial here. It's all polynomials, folks, all the way down. 7.87 plus negative 125x plus 7.23x squared plus negative 0.139x cubed to the 3. So that converts our command for like some distance in millimeters into what the command to the servo is. But how do we find that distance in millimeters? Well, we have a second plot, folks. Up here, we have throttle percent versus paddle distance in millimeters. So in our control system, the first thing that we do is we come up with some throttle percentage, right? The PID spits out, hey, we need to be at 75% throttle, okay? So what happens? We take that 75 right here, we find it on this plot, and we say, oh, 75, we need to have our throttles 5 millimeters apart for us to get 75%. So what we do is we find this data through all of the thrust that we've recorded, all of the throttling tests on the ground, all of these static fires that we've recorded. We can back out these simple functions. This one's an exponent, actually. But it fairly well defines this region of these throttle commands. So if we want 75%, we run that 75% through this function, and it gives us the paddle distance in millimeters. Then we take that paddle distance in millimeters, we run it through this, and it turns into a command on our servo, and voila, bada bing, bada boom, you have servos that give you a throttle percentage. Okay, one more thing just to interject here really quick. This is how we got those distance measurements between the paddles. The paddles have a little bit of slop in them, and so what I did is I applied a bunch of load with my finger to estimate how far the actual distance would be under load, and I just put a ruler up, and then I put the camera all the way across the room with a really tight zoom so that we didn't get any like compression stuff that would mess with it, and that's a pretty good approximation of how I got the distance between these paddles. So that's how it works with throttling. It works well enough. It didn't work amazing. There's a fly in this room somewhere. It didn't work amazing, but it works well enough, and that's what counts. Okay, moving on. I am going to get this thing. If y'all aren't subscribed to Sport Rocketry magazine, by the way, Sport Rocketry is a really good fly swatter. He's up there somewhere. No. Got him! Nice. Okay, no more fly. Next up on the list of things to talk about is TVC, or Thrust Vector Control. This is the hardware that gimbals the rocket motor and helps point the rocket in the right direction so that we can actually land without flipping upside down. Scout F ended up using 2 different TVC mounts, one plastic mount for flights 1 and 2, and then one aluminum CNC'd mount for flights 3 all the way up to flight 7, or the rest of the Scout flights. We'll get into the reasoning for this in just a little bit, but why don't we talk about that plastic mount to start? This TVC mount is printed in PLA, or polylactic acid. It's printed in 3 parts, and although PLA is usually a low melting temperature plastic, I've never had problems with it with the Estes F-15 rocket motor. The 3.5 second burn time means that the heat wave, or the heat pulse, whatever you'd like to call it, doesn't soak into the mount until after the burn is over. So it's never been a problem here. The mount goes together in an onion gimbal setup, as I talked about during the CAD section of this video, and it's pretty simple. Most of the hardware is M3.5, and we have a little pushrod connector, or a little linkage stopper, whatever you'd like to call it, on the sleeve. The servos I used in this TVC mount are the Bluebird BMS A10H servos. It's kind of a mouthful to say, but the servos are great. They're very small, they're incredibly lightweight, and they have really fast actuation time, which is generally why I select them for a lot of my projects. One thing that they don't have, though, is a metal horn. A servo horn is sort of the actuation arm that comes off of the spline of the servo. That's going to be a problem, and we'll get into it in just a minute. As mentioned earlier, the mount goes together pretty easily. We have one straight 1mm push rod that goes to one axis of the gimbal, and then one 1mm push rod with a Z-bend in it that goes to the other axis. The Z-bend is also a problem. This ended up contributing to some of the vibration calibration issues that we're going to talk about in a second. The servos connect to AVA on dedicated TVC pins, although I don't know why in this footage I'm connecting them to the fins output. That's kind of weird. And as I've started doing in most of my projects, I went a little crazy with securing the connections between cables. These servo cables can get pulled apart really easy, and I would hate to lose a flight because of a faulty connection. So I take little twist ties and I put them over the connectors. I'm sure there's better ways to do this, but I'm Joey B from BPS.space, and sometimes the solutions here are a little bit sketchy. The length of these servo extension cables is also a little excessive. I should have just purchased shorter cables. I don't know why I didn't do that, but this rocket is already such a money pit that I figured, well, I'll just shove the extra cable into the avionics bay. This ended up causing some problems with noise on the servo, nothing that would have killed a flight or made the difference in whether a flight worked or not, but it did lead the servos to jitter quite a lot on the launch pad. As I mentioned in the CAD portion of the video, the way that this TVC mount is secured to the airframe is with a screw that also goes through the leg strut mount. All of this will be covered in the leg section as well, but all you need to know here is that the screw that attaches this TVC mount to the airframe also goes through the leg strut mount. And finally, this is what the base of the vehicle looks like with all of the legs and TVC stuff attached. This is not really important for the TVC section of the video, but it's just nice footage, so I'm showing it. Now let's talk about the problems with this design. During Flight 1, the vehicle wiggled a whole lot on the way up. Actually, it's not necessarily that the vehicle wiggled, it's that the TVC mount wiggled. The dynamics that led to this event are hard to describe because I don't fully understand them, but I know that one of the really big parts of this is the slop, or the sloppiness of the TVC mount. So that has everything to do with connections that aren't totally rigid. When there's a pin in a hole or a push rod in a hole, that hole needs to be the exact diameter of the push rod. If it's any bigger, the mount can jiggle a whole lot. And when you look at this footage of me characterizing the TVC mount, you can see that wiggle is abundant. There's a couple of things at play here. One of the biggest ones is the fundamental design of this TVC mount. I want you to notice a couple of things here. The first is that completely needlessly, the servos for the TVC mount are on the bottom. They don't need to be on the bottom. It can be arbitrary. They can go up top or on the bottom. The problem is that by putting them on the bottom, even when it's just the landing motor in that TVC mount, we're not rotating around the center of gravity or the center of mass of that loaded motor. That problem gets so much worse once we attach the ascent motor as well. So in the redesigned TVC mount that I ended up making out of metal, I moved those servos up top. The other thing to notice is how much bending is happening right around here, right around where the servo is. That's because of these little plastic servo horns. I have not personally been able to find metal servo horns for the BMS A10H servo, but I bet if you looked hard enough, you could find some. This turned out to be one of the biggest problems, and I wish I had done this characterization before redesigning the mount, because I think you could get away with a plastic TVC mount with these same servos and a metal horn and get rid of almost all of the wiggle here. That said, between the Z-bend push rod, which acts like a spring, between the plastic servo horn, between the bad, rotation point of these motors, this design was suboptimal, which is why after Flight 2, which did not look so good on the way down, I decided that we needed a new piece of hardware to gimbal the rocket motor. And this is where the metal TVC mount comes in. Aluminum TVC mount, CNC TVC mount, whatever you want to call it. It's this fancy thing that I spent a very long time on, and ultimately that I don't think was worth it. So let's talk about it, because some good has to come from it. Okay, so as I said, in solving the wiggle, I wanted a stiffer TVC mount, and I decided to stop at basically nothing to achieve this, which means I want all of the material that is as stiff as possible, and I'm willing to accept some weight hits. I had this idea that I could make a TVC mount entirely out of aluminum, and I had just gotten a new Tormach 440mm in my garage and wanted to get better at using it. So I spent one whole entire week, this isn't hyperbole, it was an actual full week every day at this machine making this tiny little TVC mount. Is it good? Yeah, I think it's great. Was it worth that time? Absolutely not. I can't even show you a fraction of the footage that I shot of this process because there's so much. A lot of the complexity here too is that this type of design, this type of part would really benefit from a fourth axis or fifth axis and a much more professional machinist doing the work. I was doing this on a 3-axis machine, and while that works and you can get it done, you have to do a lot of sketchy work holding from time to time, and that caused a few problems. I also burned through a whole lot of stock material material. Again, because these parts aren't very flat, you have to chew through a lot of aluminum to actually get the part out of the stock material that you want. I had to work through designing different tool paths, things that were kind of foreign to me. It was a very good learning experience, and some of the mistakes I made were good and not that harmful. Some of the other mistakes I made were not so good and a little bit harmful. Shoot. That is not good. Ooh. Oh boy. Wow. What you're seeing here is me trying to drill one of the holes to connect the outer gimbal to the inner gimbal. I'll tell you what happens here. When your speeds and feeds are too slow, if you forget that heat exists, you think, okay, cool, I'll just go really easy on my bits. This does not work because heat builds up, and especially in aluminum, which is kind of a gummy material, what happened is I kind of welded the bit to the aluminum. I mean, for all intents and purposes, I don't think I actually welded it, but that bit is permanently stuck in there. There was nothing I can do. I tried a blowtorch, I tried pulling it out with pliers, I tried everything, and that bit was fully stuck inside the mount. So I had to take this piece, which I spent, I think, over an entire day on this outer gimbal, and scrap it, and then make a second one. The parts ended up looking very pretty, and that's good. I mean, they're metal. It makes sense that they would look very pretty. And the whole design, I am pretty proud of. I do think this is a good design. It was not worth the time to solve the problem that I needed to solve. It wasn't just the machining time as well. I also had to tap a ton of holes to get these screws to seat right and to get like the tolerances that we needed. It was really confusing to figure out which holes needed to be tapped and which holes didn't need to be tapped because we're using the screws as a bearing. And I was really nervous tapping these holes because, as you'll see in the leg development process, or maybe I'll forget to put it in, but I broke a couple of taps in the process of doing this, and usually I'm able to get them out, but sometimes you can't get a tap out. When you can't get a tap out, you have to remake the part, just like I already did once with the drill bit. Anyway, the metal mount, as I mentioned before, uses those HV93i servos. They're very nice, they're really fancy. MKS does a great job with them, and I quite like them. Overall, the mount did have less wiggle than the plastic mount, but it was really a function of those metal servo horns and taking the push rods and changing them from Z-bends and metal, like 1mm push rods, and just making these brackets or these like big, thick, aluminum, chunky push rods. That took out a lot of the wiggle. And before we wrap it up for TVC mount stuff here, I do want to talk a little bit about the TVC mount characterization. I took a Bosch B&O 055 IMU and I hot glued it to the TVC mount, both the metal one and the plastic one, just to compare them to measure the performance of the mount. This is a process that I also did for Scout E, and it's a process that I like to do for most of my models. At this point, modeling your actuator dynamics, especially on a vehicle that's this size, is a really important thing. As the vehicle gets larger, you can have a slower control system, that's all well and good. But for this size especially, having fast actuators and knowing exactly how fast they are is really important. So I used the system identification toolbox in MATLAB, and I took that IMU data, I took some time data and some step response data, and I generated transfer functions. I found the transfer function of best fit, basically. They have a lot of great tools in there, and that transfer function is what's represented in the simulation that I showed earlier. When we saw that AL transfer function thing in our simulation, that's what you generate from this IMU data. Okay, with all of that out of the way, it is now time to talk about landing legs. So, real quick, before we talk about landing legs, I want to show you something. Come with me on a journey. This right here is Adobe Premiere. This is the project that I'm currently editing. You're about here in the video right now. You've just seen me talk about that we're going to talk about landing legs. These are the other sections of the video. You've got a section where we talk about throttling. I've got a section where I talk about simulation. I've got a section where I talk about CAD. Right here, see these numbers up top? We're at about an hour and maybe 25 minutes into the video, something close to that. I'm going to scroll out here and show you the landing leg footage that I have. Let's just scroll out here, scrolling out. This is the end of the landing leg footage. Do you see this number? That's 7 hours. There's 7 hours of landing leg footage. Who did this? This is what we call in the industry overshooting. I shot way too much footage of the landing legs. There is like no way that I will be able to properly show you all of this production footage, all of this test footage. There's so much content here, and I don't know how to deal with it. So I just want you to know I could put together a 7-hour video with landing leg stuff, but I'm going to spare you because I don't have the time to edit that and you don't have the time to watch it. Okay, with that said, let's talk about the legs now. So these legs were some of the first parts that I made on my Tormach 440 mill. I love this mill. I'm having a great time using it, but it did take a little while to build the parts, and I probably made more of them out of metal than I really needed to. First up here is the strut mount. The strut mount is covered a little bit in the thrust vector control section, a little bit in the CAD section, but it's the part that feels all of the compression load when the vehicle slams into the ground. It's made of 6061 aluminum, and it's a pretty simple part. The next parts that I made were all of the little tiny brackets. These are the brackets that hold onto the carbon fiber spars that are parts of the legs. These are the brackets that terminate the struts of the legs too. There's a lot of little tiny parts, and I tried to mill them out of one big piece. This did not work great. I shot a lot of time-lapse footage of this, and I wish I had shot real-time footage so that we could hear the audio, but I broke at least 2 bits making these parts. The feet of the legs, or the ends of the legs, are made out of PLA. They're 3D printed. I kind of intended to make these metal originally, at least that's how the design was set up, and then when it came time to make them, I was like, we have enough metal parts in this rocket, we can just make them out of plastic. Next up on the list of parts to make is the leg base, and this piece is kind of a nightmare. I milled it out of 1/2-inch 6061 aluminum stock. I had to make this part 3 times before I got it right. I don't remember what exactly was wrong with the first part. I think we measured our Z height on the mill just a little bit wrong, and we cut through too much material or not enough material or something like that. So that part had to get scrapped. Then I made a second part which came out perfectly, and as I started tapping the holes for the part, I don't have good footage, of course, of it, I broke a M2 tap, it's a 2mm tap, inside one of the leg attachment holes. This part has 20 holes that you have to tap in it. There are 12 that are M3.5, those are pretty easy holes to tap, and then there are an additional 8 that are M2, and so those holes are really hard to tap, and if a tap breaks inside one of those holes, the part has to be scrapped. There's not enough space to like drill out the tap or do it in a bigger size. It's it's really like I'm working with the minimum amount of metal here, and so it's easier to just redo the part entirely. Anyway, really good learning experiences all around, but very frustrating in the moment. There were a lot of operations here that also would have benefited from a 4th or a 5th axis here on the mill, but since I didn't have it at the time, what I did is I 3D printed these little jigs to hold parts so that I could effectively drill on a drill press or a hand drill. You can see some footage here of me drilling out holes on these brackets to hold the legs and the struts. Later on, I end up tapping these holes, not because we have to put an actual screw in there, but because when we epoxy the carbon fiber struts into the hole, you can get really good bonding or surface adhesion on the carbon fiber strut end of the problem. But if you tap the hole, you create lots of mechanical ridges, and you actually create more surface area for the epoxy to grip onto, especially since some of these parts end up in tension. Tapping these holes before you epoxy the carbon fiber rod in turned out to be a really smart move. One super quick caveat to that, though, you have to get rid of all of the tapping oil. Any type of tapping fluid, cutting fluid, whatever, it has to be completely gone. I soaked these parts in acetone for a long time. I ran a lot of solvent over these to make sure that we got rid of all of the tapping oil, because any improvements that you make because of this tapping, you're going to get rid of them if you have that tapping oil on there. That is going to completely prevent having a good bond there. So that's the only caveat to this. For the leg base, I had to use a hand drill to drill out the leg attachment holes manually. These holes are not completely perpendicular to each other because the legs are sort of at an angle. You know, you're like 95 degrees, 97 degrees, something like that. And so having this little 3D printed drill tool allows me to make those drills at just the right angle in just the right position every time. There's quite a lot of footage of me epoxying these parts in place. I used Loctite High Sol for this, the same Loctite that I use on fin fillets, on other epoxy operations. It's one of my favorite epoxies, and it works quite well. Now, there's a little bit of slop or a little bit of wiggle room in the size of the holes versus the size of the carbon fiber rods, especially since I tapped those holes. So what I did is I epoxied all of the leg parts at the same time. I assembled the legs as they would be in terms of how straight they would be and, you know, the attitude of all of the parts. And then I laid them out to dry for like 2 or 3 days just in this position so that they would all be centered when they cured. I did some initial deployment tests by just cutting the rubber band with a pair of pliers, and then once that looked good, I took the vehicle outside, or rather, I took what is a mass and inertia mock-up outside to see how well the landing looked on some cardboard. I've talked about this before, but the original plan for Scout was to target a landing on a landing pad. The landing pad was comprised of several different layers of cardboard, and I arrived at this design, if you want to call it that, by just dropping the rocket a whole bunch and then seeing how much cardboard it took to arrest some of that bounce that's inherent in a really rigid structure like this. I also found that a layer of Mylar on the top of the landing pad let the rocket slide just a little bit on touchdown. This is a really helpful thing because if you can't slide, you end up tipping over. Ultimately, though, as you'll probably know if you're watching this far into the video, I'm sure you know it by now, but we ended up removing the landing pad from Scout F because between the inertial guidance, or like the dead reckoning ability of Scout, the positioning ability, and the actual control ability of the vehicle, we could not target a landing pad as I thought we could. So we just had to touch down on the dirt, which means that we still had that bounce problem. So what I did for that in some of the later flights is I attached some linear dampers to the struts. I cut the strut just a little bit shorter, and I tried out several different linear dampers, all the while crying for my wallet as I bought them from McMaster Carr. And it turned out that these little guys, these little linear dampers right here, they worked pretty well, so I ended up attaching them to the end of the strut. If I were doing this again, and I had to use almost all of the same parts, I would attach just a second linear damper. We have about 5 millimeters of travel on these linear dampers, and I think bumping that up to 10, if we put 2 of them back to back, that would have made a big difference in terms of the touchdown dynamics of the vehicle. But, you know, live and learn. To cover a few other things here, the landing legs are held back by a rubber band, which gets cut by a nichrome wire that the flight computer sort of fires or sends lots of current through. The only time we've had this fail, at least with the Scout program, is on Flight 4. I set the deployment altitude just a little bit too low, and there's a deployment altitude, but then there's a safe altitude. And if you move into the safe altitude, which means you can't fire any pyrotechnics, it'll shut the leg deployment off. I had also switched to a less powerful battery on that flight, which means that you can't send quite as much current through that nichrome wire, and the wire was a little bit longer. So this is not a very reliable solution. I think in the future it would be nice to have something that's a little bit more repeatable and less, you know, relying on expendable parts. One other thing to cover here too is that the landing leg base was never really manufactured correctly. The base that we ended up flying with, I think I was missing about 1 millimeter of aluminum at the bottom, so I must have messed up something with my Z height measurement when I did the milling operation, because in some of the later flights, I noticed that the legs were folding out way too low, and it was because of the little corners that hold the legs up. The leg base is what sets the deployment angle of the legs, basically. That's where the stop is, that stops the motion of the legs flipping out. And that motion is pretty violent. With the thin metal that was trying to stop it, I ended up ripping through that aluminum. And so in later flights, what I did is I cut out, you know, essentially a piece of the bottom of the landing leg mount. I just milled it out, and then I epoxied the whole face to the bottom of the vehicle to essentially just add a new piece of aluminum down there, and that seemed to work well enough. If I were doing this again, I would like to do it with a different leg design. These legs do work, but if you're not targeting a landing pad, you need some way to absorb that shock. It turns out it doesn't matter how many times you can get close to the ground at a low velocity. If you don't have good legs, you're gonna tip over every time, and it is so frustrating to do that. So if you're doing something like this, Spend the time on the legs. Spend good time on the legs. All right, so with all of this covered about the landing legs, let's move on and talk about avionics and telemetry. In terms of avionics, the star of the show for Scout is AVA, which is a computer that I built back in 2020, or at least I designed it then. I've manufactured it a couple of different times in slightly updated revisions. AVA stands for All Vehicle Avionics, and it does exactly as you would expect. It flies everything that I build. It flies Scout, it flies on high-powered rockets that have control, it flies on high-powered rockets that have no control, it deploys parachutes, it does all sorts of stuff. I designed AVA back in 2020 with the goal of never needing to design another flight computer for at least 5 years, and so far, it's working out pretty well. Specifically, in terms of sensors that we use here, we have an IMU, which is the Bosch B&O 055. We also have a high-gravity IMU and a backup IMU, neither of which are that important, but the high-gravity is the KX134, and the backup is the LSM-60S3. We have a barometer on board, which measures the air pressure and helps us figure out what our altitude is, and that is the TE MS5611. It's a pretty fancy little sensor, but it's very accurate. It is not, however, accurate enough to do all of the stuff that we need. We can't just use the barometer alone. It's a very noisy sensor, as you can see in some of this flight data here. So when we're looking to find out how far above the ground we are or how far downrange we are, we use a few sensors and then fuse them using something called a Kalman filter. We'll talk about that in a second. To wrap up the sensor portion of this, we also use a GPS on board, which is the U-Blox Zoe M8Q. The GPS is the same story as the barometer, which is that it gives us good data. It's helpful to know where we are in terms of latitude and longitude and GPS altitude, but it's not good enough on its own. So the barometer, the GPS, and the IMU all get combined in this Kalman filter. I've mentioned before that Scout uses dead reckoning, which is that we just trust the IMU implicitly from the pad, and this is sort of true and sort of not. When I say that we're using dead reckoning, I mean that we are still using a Kalman filter. We're still fusing the accelerometers with the GPS and the barometer, but we're mostly trusting the accelerometers, almost exclusively at this point. The flight time is 10 seconds, and over the course of those 10 seconds, if the GPS and the barometer stayed at 0, it would affect our altitude a little bit, but we would pretty much have a normal flight. Actually, we would have an almost entirely normal flight too, because the Kalman filter does a lot of error checking at this point to make sure that the data that we put into the system is valid. And so if the GPS were giving bad data, we would just reject it anyway. Back to electronics though, we have a couple other things going on. We have some cameras on the rocket, and these are RunCam split hybrid cameras. I don't really know what the exact name of these cameras are. I've seen them listed in a bunch of different ways, but they are very good. Okay, they're actually called FPV 4K Camera RunCam Hybrid 2 HD Recording Camera with Dual Lens Phoenix 2 Analog FOV 145 degrees QR code parameter settings 18G Micro FPV Cam for FPV drone and RC hobbies. It doesn't matter what they're called. It's just the one with the two lenses, and it also can shoot 4K sometimes. There is one camera that's outside the airframe pointed downward, the down-looking camera. That's a RunCam split hybrid, and it's recording at 120 frames per second and 1080p. That's really good for the size of the camera. For flights 1 and 2, I also had another one of those RunCam split hybrids that was mounted on the back of AVA that was pointed directly down at the TVC mount. This was a really cool internal view when we did Scout E and we ejected that motor, but on Scout F, it doesn't do that much to see the movement of the TVC mount. And I really needed to cut back on the weight budget, so I ended up removing it for flights 3 and onward. In terms of the power here, or the battery that we're flying on the rocket, I'm pretty stingy about this stuff, and I cut it a little bit close sometimes. The original LiPo that I flew with was a 2-cell LiPo with I think 500 milliamp hours of capacity, and then after flight 2, when I needed to reduce a bunch of weight, I switched it down to a 300 milliamp hour capacity battery. In terms of current draw, on the launch pad when the vehicle's just idling, we're not gimbaling, we're not moving servos, the static current draw is somewhere around 400 milliamps, so it's a little bit close. We can idle on the pad for about 30 minutes before it's a real problem. I also carry a LiPo charger with me to every launch so that I can test the vehicle, then reboot it, charge the battery again, and then turn it on for flight. While we're talking about power, most of that power is going to those run cams. It's going to those hybrid 4K, whatever you want to call them, cameras. They draw quite a lot of current, and they actually hate being at 7.4 volts. You're sort of teetering on the point at which they will shut off. Some of these cameras advertise that they can work at 5 volts. I have not found that to be that reliable. So what I actually did on the last few flights of the vehicle is I added in series a second LiPo, just a 1S LiPo with like 100 or 200 milliamp hours to the camera circuit. And so the camera ended up at 11.4 volts. It was a little sketchy circuitry-wise, but it did seem to work and it improved reliability. We ended up having a few flights where the camera straight up did not record because there were voltage spikes or something that flipped the camera off and it couldn't turn back on. Moving back down to the avionics and control part of this whole situation, you'll notice that the avionics stack looks kind of bizarre. It's got this big carbon fiber rod or spar that sticks out from the top of it. I talked a little bit about this in the CAD section of the video, but the purpose here is to physically separate the telemetry radio, which is an XB Pro S3B, and the GPS antenna, which is a generic helical antenna. We want to physically separate the radio, the telemetry radio, and the GPS antenna physically from each other, and also both of them from the avionics stack. There's a lot of sensitivity in there, and RF-wise, it's kind of a mess. I sort of maintain that I don't think GPS is necessary for this type of flight. It's 10 seconds. You can totally get away with just integrating your accelerometers, but when I designed this rocket and I built the avionics stack, I included the GPS in there. It's kind of locked in the code base right now. And so I left it on for the future flights. You would want GPS, and especially you'd probably want RTK GPS or differential GPS if you were going to try targeting a landing pad. But for this, if you're landed anywhere, it should be no problem. Now, speaking of telemetry, that XB broadcasts telemetry at 915 megahertz. It is a 250 milliwatt radio, which is not that strong. This is the same radio we tried to use on Lumineer, and I did not do a proper link budget, which is why the telemetry cut out mid-flight. Either way, for Scout, we're only going to 30 meters, and so 250 milliwatts at that distance is like way overkill. The ground station is ultimately a version of the ground station that I wrote way back for Sprite in like 2019. I wrote it in a program called Processing, which is great for learning code. It's not really good for building something that's this big and this complex, but it works, and I needed to build it quick, and it turns out when you build solutions quick, sometimes they stick around and haunt you forever. For a little while, I also had a ground station for some of my high-powered rockets written in Python, generously done by my friend Joey Murphy. But for Scout, because we're using largely the same software as we were using in 2020, it was easier to just continue using the Java version or the processing version for these flights of Scout F, rather than port over all of the changes that we had to make for the Python version. That pretty much brings us up to speed on all of the avionics details, minus a whole lot of stuff about AVA. If you want to learn more about that flight computer and all of the details about how it works, why I selected sensors, etc., there's a video from when I designed it down in the description below. It's like 20 minutes long. It's got a ton of detail in there, and you can check that out if you want. And moving on here, let's talk about the reaction wheel for Scout. Okay, besties, it's time to talk about reaction wheels. Okay, so here's the deal. We control the pitch and yaw with the TVC mount, right? We gimbal the motor and we can control this and this, but we can't control the roll axis if we don't do anything. Now, in a perfect world, that's not going to be an issue because there's pretty much no roll torques coming from the motor, right? Sometimes. I have had several flights in the past when I didn't use a reaction wheel where the motor did appreciably spin up the vehicle. I don't know exactly how that phenomenon works, but I would assume there's some channeling that happens in the nozzle and we create some roll torques. Now, that even still is not a problem on its own. The problem is when we spin really fast, our servos cannot keep up quite as well as they could if we aren't rolling at all. So the reaction wheel is about trying to minimize that problem. We can control the vehicle if it rolls around. We do all of our guidance and stuff like that in the inertial frame. So it's not a problem if we have some body roll, but we want to control it. And that's what the reaction wheel is all about. Mostly, though, we want to control how fast we're rolling, which is we want it to not be very fast at all. Okay. That's all the details about that. I talked a little bit about this in the CAD section of the video, so I guess there's not a whole lot to cover. But we use a 12-volt DC motor to drive this reaction wheel. This is the cheapest motor I could find on Amazon. It works just fine for this scale. It's definitely, like, not ideal. I wouldn't do this if I were redesigning it from the ground up, but I know that it works well enough, and I have gains, like PID gains, that I know that they work well enough. So that's why I keep choosing it. As for the wheel itself, initially I made the wheel and housing on my Tormach 440 mill. This is another thing where I wanted a lot of practice with the mill. The housing certainly did not need to be made out of metal, and frankly, the wheel didn't either. But as I build bigger parts, there are parts that need to be made out of metal, and so I wanted to get practice with smaller pieces. The wheel has 3 spokes in it. I didn't do anything to balance the wheel because we aren't spinning it that fast, so a little vibration is not a big deal. And the housing is a piece that I'm quite proud of. It looks very nice. Initially, I wanted to heat shrink fit this wheel onto the shaft, so I slightly undersized. I'm talking like 1 or 2 thou undersized the wheel hole to fit on the shaft. And that did not work at all. I put a blowtorch to it. I tried not to melt the aluminum, of course, but it did not work at all. And I think in hindsight, what I did wrong is that a shrink fit at that scale, you're not going to expand the metal that meaningfully. It works much better, I think, with much larger holes. So what ended up happening is I just used a hammer, some percussive persuasion, and I press fit it onto the shaft. And there's not a whole lot more to cover with the reaction wheel. I just thought I would tell you some details and show you how I made it. So let's move on. All right, let's talk about integration. Everyone's favorite thing, integration hell. It's not that bad for Scout F, but it's not good. I hate integration on this rocket. I think this is probably true for any project, especially rockets, where integration is like part of the procedures. There is a direct trade-off between your mass and your ease of use. The lighter weight your vehicle is, the harder it is to work with. This is true in a couple of different ways. Like, it's definitely true in a control systems perspective, but it is also true in terms of integration. By the way, when I say integration, I'm talking about putting the avionics into the vehicle, putting the reaction wheel into the vehicle, moving things around between flights. I have to remove the whole TVC mount between flights so that I can mount a new motor in there for landing. I have to reinstall this whole throttling mechanism. There's all this weird stuff that has to go on in the background that doesn't really get seen. And I'm so convinced that there is it is like a law of the universe. There's a direct trade-off between how easy your rocket is to work with and how light it is. I would love more than anything to do another version of Scout that is built kind of like a lot of liquid rockets that I see right now, or a lot of student-built liquid rockets, which means you've got a ton of C channel, or you have a ton of structural interior, and then you have an aesthetic exterior that's just focused on aerodynamics and stuff like that. So that when you want to work on the rocket, all you do is you pull that C channel out. You just move the whole internal of the rocket external. What we have right now, though, is a bunch of different parts that are attached at a bunch of different points with these screw holes. And so you're like moving around the avionics stack and you're like trying to figure out where the screw hole is before you screw it in, and it looks really great and beautiful in the footage, and it is such a pain to actually do in real life, especially with that TVC mount. The other problem with integration is cable management. Cable management gets a little bit tricky at the small scale, especially when you don't have a whole lot of space inside the airframe. Remember how that CAD looks where the avionics stack is right above the TVC mount? I want you to think about what happens to all of those much larger servo cables and the big plastic pieces. There are 4 of those plastic servo cable things that have to sit somewhere in there, and they have to not interfere with the top of the motor as it's gimbaling back and forth. TVC jams have been a problem for me in the past. I don't think Scout F ended up having any, but I worked really hard to try and mitigate that. What does that look like? Honestly, because you can't see inside the airframe, it just looks like a bunch of jostling them around. Another thing that just sucks about integration here is managing the cables that come outside of the vehicle. So we have at least 3 cables that have to come out of the avionics windows on the side of the rocket, which, by the way, is already a mess in itself. Having holes that big in your rocket is not confidence inspiring. Either way, when I want to take the avionics stuff out, I don't have good access to the screw terminals on AVA, so I have to take all of the cables that come out. That is the landing motor cable. That's the landing leg cable. So there are two different pyro cables there. There's an arming cable, and then there's a battery cable. So I suppose there's four. I have to take all of those and shove them into the airframe, just hoping that they don't like contact each other in a problematic way. Before you offer solutions for this too, I totally understand that there are better ways to do this. Like you could put a connector in there, you could make a wall segment that's on the side of the avionics bay. There are ways to fix this stuff. But it gets heavier as a function of those ways. Adding connectors adds weight, especially at this scale. I had an XT30 or XT20 connector that was connecting the camera from the top of the vehicle to the bottom of the vehicle. I took it off and it saved like 8 grams, which is huge at this scale. This rocket is 1 kilogram and I am definitely counting individual grams here. Also, moving around a rocket with these big spindly legs is kind of a pain too. If the legs are out, you risk bending them, you risk breaking some of these joints on the metal base, like the leg base, which is terrifying because of how long it takes to produce the leg base. And then if they're folded in, it can't like sit nicely on something. Again, because these legs are so spindly, you can't like put it on a nice surface and just let it rest. So it's always kind of stressful to work on this rocket. Anyway, there's not too much else to cover in terms of integration. It's all stuff that I've talked about before where I'm zip tying any joints between cables. There's a lot of hot glue on AVA that's holding those servo connectors into the computer. So if I accidentally tug on one of the servo connectors, it's not going to risk disconnecting it. That's pretty important. I've also become a pretty big fan of the idea of arming the vehicle by twisting the two arming cables together. You could put a switch there, but again, ease of use and mass, a switch is heavier than just 2 strands of wire that you twist together. I'm going to wrap up the integration section of this video because at this point it is just a rant. So let's move on. All right, and the last thing to cover here as far as the build process goes is painting. Painting is always one of the harder parts for me of rockets. Not only does it require some skill, but it requires a ton of patience and planning ahead. 2 things that I'm not excellent at. I opted for semi-gloss paint with Scout. Semi-gloss is a really nice blend of flat paint and glossy paint. Flat paint is really nice, but it doesn't really sparkle in the sun. And glossy paint sparkles real good, but it takes forever to dry. That enamel can take up to a month to fully cure and fully harden. And I did not have that time when I was building this. So semi-gloss dries to the touch in a little bit, and after 24 to 48 hours, you're pretty much good to go. I like adding these roll stripes on the rocket too. What I do is I just put on tape where I don't want the paint to go, and then add the roll stripes that way. They're not super precise, or they don't have to be an exact size, but they do actually help quite a bit with the digital tracking that I like to do. I like to go in post-production, digitally stabilize the vehicle so that I can see the exact attitude, and it allows me to understand a lot more clearly what the rocket is doing in flight. Sometimes these things are called fiducials. You'll see them all over rockets, especially in the test campaign, especially like right now SLS is on the launch pad, and they've got those little fiducial things, those little black and white checkerboard things, everywhere. When this thing launches, they're going to use all of the camera angles that they have to digitally stabilize or basically get a reference for exactly where the booster is, each part of the booster, and they'll be able to see the flexing, they'll be able to see the vibration, and at a much smaller scale, this is what we do on Scout. In terms of labeling and text and logos for my rockets, generally I'll go one of 2 ways. Sometimes for larger rockets that go really high and fast, I'll actually paint on the logo. And I'll do this by either ordering or making my own stencil, applying the stencil to the vehicle, doing a really careful spray paint job, and that lasts a really long time, and it's really good if you have a lot of patience. But especially with white or black rockets, you can actually use printer paper, and that's what I do for Scout F here. I just print out the word Scout, I print out all of the little labels that I want, and then I use Super 77 spray adhesive to attach those pieces of paper. This is easier than a decal, and it's essentially what you might call a 5-foot paint job. Once you're far enough away from the vehicle, you can't really tell. Especially in those tracking shots, you kind of have no idea that that's a piece of paper and not actually painted or stenciled onto the rocket. Once the logos were on, one of the last things to do before launch is, with the vehicle integrated, the whole whole thing painted, it's ready to go, I remeasured the inertia of the rocket. The mass moment of inertia is sort of a measurement of how hard it is to turn or move an object. In the case of Scout, imagine that I had concentrated all of the weight, all of the mass right at the center of the vehicle, and so while it's still about 1 meter long, all of the mass is concentrated at the center, so it's really easy to rotate. And now imagine that I put all of that mass at both sides, at both ends, so in that setup, it's a lot more difficult to rotate the vehicle, and measuring the mass moment of inertia is basically what we're doing here. The way that I do this is called a bifilar pendulum test. You can learn a lot more about this from physics lectures, and there's a bunch of good material online about it as well, but the bifilar pendulum test takes advantage of small angle approximation, the gravitational constant, and we use all of these things along with a lot of careful measurements of the ropes that we use and the exact timing of each rotation to determine what the mass moment of inertia of the vehicle is. And with all of that stuff covered, that pretty much brings us up to speed on how I built Scout F. If you want more details on how the flights actually went, there's a bunch of good videos that are linked in the description down below of the actual flights. You can see me progress from Flight 1, Flight 2, Flight 3, Flight 4, Flight 5, all the way through Flight 7. And if you want more details on past Scout programs too, there's a similar engineering cut for Scout E, the previous version of this rocket. There's actually a lot of similarity here too. Scout E uses the exact physical same computer and a lot of the same avionics mounts and things like that. As I mentioned in the beginning of the video, if you want to build one of these rockets yourself, hopefully this video helps. And if you want the actual step files, the physical CAD files for these parts, all of these parts on the rocket, those files are linked down below on Patreon where you can support this project. Anyway, I hope you enjoyed this video. This is not the type of thing that should, in theory, succeed on YouTube, but I think it's really nice to make sure you document as thoroughly as possible all of the details of a project so that 5 years, 10 years down the road, you can go back when you can't remember any part of it and you've got it all documented. So that's the purpose of this. I hope it helps you, and I'm sure it's going to help me in the future. I frequently reference the past engineering cut for Scout E. That's all I got for now. Thank you very much for watching. My name is Joe Barnard. May your skies be blue and your winds be low.